My background is I have a bachelor's in geology from Cal State Northridge, and worked as a geologist for a couple of years in geology. Realized I was far too immature for a real job and became a fireman. Did that for 25 years, and then my body said, you can't do this anymore, and I retired. I didn't do any real geology for most of that time, so all of the good stuff they taught me in 4 years of intense instruction has pretty much been forgotten. And what we have left, I can squeeze into the 2 hours that we have. So that's all you're going to get. The thing about geology for me is I was working as a wilderness guide, wilderness instructor for the school, and when we were walking through the Sierra Nevadas, people would go, "What's that?" And then I'd say, "I don't know, it's a rock." So I took a geology class. In that geology class, I approached it with great trepidation because everything I knew about geology was memorize 200 rocks, memorize 200 different time scales, memorize 200 different fossils. And I'm terrible at memorization, so I was going, this is going to suck. Okay. And then I got into the geology class, and this little thing called plate tectonics took geology, which was just random events in the history of, let's say, the Appalachians. They'd go, the sea came in, the sea came out, the crust got crunched, mountains came up, mountains got worn down, and then it happened again. And the question was, why? Don't know, it just happens. And they call it the geosynclinal process, but nobody knew why it happened. Well, when you understand plate tectonics, now we know why it happened. 2 continents went bang, and that's what caused things to crash together. And then they started explaining, well, how do you know that? Well, the density of this rock is different from the density of that rock, and da-da-da-da-da-da. I'm going to spend 2 hours now giving you that framework that makes geology make sense over time. Okay, and that's about all we're going to get. You have a little cheat sheet. It is, most of it's going to be subject to test later on, but you do want to pay attention. But we're going to review it at the end to make sure that you have what's important. You're going to end up with 3 names for kinds of rocks, 3 different rock names for rocks. I can get you some more handouts. Okay, so we're going to have names for rocks based on how they're formed, names for rocks based on what they're made out of, names for the 4 major time periods through geologic history. And so it's pretty simple stuff, and it'll make sense as we go forward. Okay? When I think about geology, the thing that helps me become a geologist is processes rather than memorization. So a lot of what we're going to work on today, come on, there we go. What we're going to work on today is not memorization, it's understanding the processes that make the world work, and those processes have not changed over time. So stream channels are shaped like a V, glacial channels are shaped like a U. Okay, those processes have worked the same because physics works the same over time, and it works over a long period of time. The things don't happen very quickly unless you're going to talk about perhaps climate change. Okay, process over memorization. Okay, the things that you're going to get off your list are sedimentary, metamorphic, and igneous rocks. Everybody heard those before? Yeah. Okay. Feldspar, quartz, mica, and calcite. Now, everybody heard of those? Okay. Somebody here's lying, because most of us are not. Okay. All right. And then those are the most common minerals that we're going to talk about. And then the next one down is rocks based on what they're made out of. Granitics, conglomerates, gneiss, and limestone. Those are the rocks we'll find here. We're going to go for a walk later, and you'll all be able to point out, yes, that's conglomerate, that's a limestone, that's a granitic. And then faults. Earthquake faults define life in Southern California in many ways. How many people here have 3 days worth of water in their house. Okay, those are people who have heard my lecture. You all know what we're done. Okay. The other thing that I have done for many years is teach community emergency response training. And that's based on the fact that the fire department is not coming after the big one. You are going to be on your own. And if you don't learn any of this and you get water in your house, your time will have been well spent. Okay? I am a firm believer in smoke detectors and water for earthquake preparedness. So we'll come back to that later. All right. So the processes that brought everything together, like I mentioned before, is plate tectonics and the rock cycle. As the surface of the earth goes sliding back and forth across the mantle, crashes into different places, gets subducted, the rocks get moved, put into environments, and changed. And the rock cycle is what makes that all happen. Okay, so this is our home. It's got an inner core, outer core, mantle, and the crust. In this picture, you can see the crust. If it was to scale, you couldn't even see it. The crust is divided into two main types. There's a crust where it's a continental crust and a crust in the ocean. The ocean crust, oceanic crust, is only about 5 miles deep. And then you're into mantle. It's about 70 miles deep underneath the continent. All right, so rock names. I got ahead of myself. Sedimentary, metamorphic, and igneous we already talked about. And then when we talk about what it's made out of, this is chemistry. Anybody like chemistry? Okay, you guys can help the rest of us with the chemistry. Okay. My daughter is about to graduate from Cal State Northridge. Somebody asked her what a year and a half ago, what's the coolest thing you've ever seen? And she said the periodic table. I read the learn. You don't have to learn the periodic table. There are just going to be a few atoms that you have to figure out in order to get through it. All right. That's for sedimentary rocks. That's kind of out of order. We're going to come back to it. Okay. Igneous rocks. The way to remember, first way to remember the names of the rocks or how they form. Sediment, settle out. So you've got stuff that's either being carried by wind, water, or glaciers, and it drops out and stops and gets buried and becomes a rock. That makes it a sedimentary rock. Igneous rocks are things that have melted to the point where it's one homogeneous broth of stuff. Okay, so the way I help people remember it is igneous is so hot it would ignite things. And this is lava off of a volcano, and we're used to seeing that. This, when it's flowing like this, it's what we see out of the basically coming straight up from the mantle like we see in Hawaii. It's called extrusive. This stuff gets outside and it cools so fast that it doesn't get to time to form crystals. If it is inside the earth as it cools, then small crystals grow, and we'll come back to that later, and you get rocks like we see in the Sierra Nevada. In between the two, settles stuff that can settle out, you still see the particles, stuff that melted all the way and is coming out of a soup, you have metamorphic rocks. Okay? So when we talk about, and this is obsidian, we don't have much of it around here, but it's a common rock that people will see. This is an intrusive igneous rock. In this case, it cooled so slowly that the individual crystals of different kinds of minerals had time to form and separate and within the earth. All right, and there's the in-between rock. You guys have seen the fancy rocks that are on the that they transport out and that are on the chimney. This has some limestone and some other stuff, but that's obviously been smushed. Okay. All right, so how does our world get built? Big Bang, suns. Everything was helium. This is vastly simplified, but it'll work for us, for what we don't need to know for making this class work. Okay, everything is helium, and then suns form, get super hot, we have cold fusion. This is not something you need to memorize. This is the framework that helps it all hold together. Okay, Inside the suns, we have fusion. That creates a bunch of heat and energy. Hydrogen gets together and becomes helium. Heliums get together, a bunch of those become carbon. A bunch of those get together and become nitrogen. And it keeps building atoms. So everything around us that isn't helium is the result of a previous star doing its thing, blowing up, scattering its molecules around and atoms around space, recombining, and voila, here we have our planet. Okay? So atoms are the simplest thing. An atom is defined as the simplest, smallest particle where you can define physical characteristics of that product. So oxygen atoms are different from helium atoms. Does that make sense? Doesn't anybody yet? Okay, the one other thing I forgot to mention is that I will occasionally get so involved in what I'm trying to tell that I will lose track of what I'm saying, and it becomes very confusing. Please, do your friends a favor, stop me. I will back up to the place where I stop speaking English, and we'll go on. All right? So, atoms are simple. When you get all atoms of one kind, all, let's say, silicon, together, and it's just silicon, that's an element. Okay? Some of the items in the kinds of atoms that are in the periodic table are solid at room temperature. Some of them are gaseous. But when they combine with other things, then they may all become solid at one time. So, atoms of all one kind of atom, let's say that we count the number of protons in an atom to tell what it is. So, all the same atom is just an element. When we start to mix atoms from different, mix atoms from different elements together. So we have, let's say, oxygen and carbon. They get mixed together. Then those will form a molecule. When you get a bunch of molecules that come together and they arrange themselves in a special proportion, they become minerals. When you get a bunch of minerals that are now mixed together, those become rocks. When you get a bunch of rocks together, they become landforms, and then we get to earth processes. Okay, really fast, kind of confusing. Anybody feel too lost to go on? All right, so jumping back to atoms and how they form both molecules and crystals. One of the coolest molecules that you're going to get is common table salt. Okay, and the reason it's common is because you've got sodium and chloride, and they pack together very, very well. In order for salts to form, all you really have to do is have water precipitate out. If the water precipitates out slowly, the atoms have a chance to bounce in and settle in exactly the right place to form the salt crystals, and you get good big crystals. If you took your salt water, put it on a frying pan, and boiled the water off very quickly, you wouldn't have big crystals form, you'd have lots of little ones. Okay? In the earth, we get the same sort of thing happening. Inside that big magma chamber that used to be underneath the Sierra Nevada, we had a mix of a bunch of different chemicals that were all trying to find a place to settle in as it cooled. If it's hot, then things are bouncing around and it's a liquid. As it cools, they become solid. As it becomes solid, slowly, the atoms have a chance to get into their preferred least energy orientation, like this, and become a crystal. Okay? So one of the things that you see in a crystal is the orientation of, the proportion of the atoms. For this, it's 1-to-1 sodium and chloride. For other minerals, it'll be something else. But you also look at how the minerals pack. When I was in chemistry, the chemistry teacher said, geologists are all crazy. They not only have to remember what the proportions are, we have to memorize what the orientation of the crystal lattice is, out of, 9 different types of crystal lattice, and how the light goes through that and gets refracted and all sorts of stuff. And yeah, it's pretty tough to get through those 4 years. But when you do, you can bore people to death. Asking what my wife is geologist to do. Just a question, yes.
So the definition that you just gave us of how minerals clump together, would that then explain why you would have veins of gold or silver?
Okay, everybody hear the question?
Yes.
Okay, and the answer is, good thought, no.
Oh.
The veins of gold and silver will come back to later, but basically it's because you have solid rock and cracks in it, and the fluids flowing through those cracks now are bringing new elements, usually things like water, copper, gold, silver, iron, and as those are flowing through the crack, they have precipitation that drops out the minerals, and that's where the preferential location of the ores are. Okay. All right. So we got sodium chloride. I've wandered a little bit more behind, so I'm not going to do my demonstration. But if you notice, the sodium chloride here is a cube. You can do an experiment where you can fill out table salt and then put I'll show you what's going to happen if I'm not. Okay. Salt, table, rounded edge. You put enough salt down here, it creates a pile, and then you can put this down into the pile of salt, and it will balance. And the reason it'll balance is that you're creating a little structure where all of the square shapes build a solid foundation for your thing. I'm not going to do that because it makes too big a mess. But trust me. Okay, so talk about crystal structure. We see crystal structure. We hear about it in snowflakes. Every snowflake is unique. Okay, so we don't have to worry about that. Our geologists don't have to worry that hard. We deal with a slightly simpler world. Okay, so let's get down to what's the world made of, what's the primary component. It's going to be silicon, oxygen, and a bunch of other stuff. Silicon and oxygen, when they come together, form the silicate tetrahedron. 1 silicon, 4 oxygen. You don't have to know this. What you do have to know is that it tends to form this tetrahedron, which is like a pyramid. And then these pyramids are the building blocks of the silicates, which are the primary kind of rock on Earth. Remember before we had silicates, carbonates, and evaporites? Silicates are the main thing. This, when you get silicon, or silicate, tetrahedrons, and you get a bunch of them that have a chance to slowly form a crystal, it'll look like this. Okay? Those crystals have a couple of characteristics that we're interested in. The first one is the orientation of the atoms and how they stack. Very important when we look at mica. The next one is, what's the surface of the crystal look like? And the third one is, are there any places in this where it's weak and it tends to break? Okay? So, if that's what silicate, pure silicon and oxygen get together and form silicate tetrahedrons, the tetrahedrons form quartz. Okay? Quartz crystals look, I'm sorry, that's not a great picture. You've all seen the quartz crystals where it's 6-sided and it's got shape. Okay? That's a crystal face as it forms. The thing that makes quartz easy for us to recognize in the field is even though it may change color based on the contaminants that are in it, a little bit of copper changes one color, a little bit of magnesium it changes to another, doesn't matter. Quartz, when it breaks, is not going to have a cleavage plane. It looks like glass. So if you're looking at a rock, and rocks